There's a liquid you can make at home for under $2 that turns ordinary sand into a block of artificial stone harder than most concrete you have ever walked on. Not mixed into cement, not poured into a mold with industrial compounds. Sand. Plain sand you scoop from a riverbank or buy at a hardware store for $3 a bag. You combine it with 2 ingredients that your grandparents kept in the kitchen, and within hours, the grains fuse into a dense, load-bearing mass that resists heat, resists moisture, and resists time. Builders in the ancient world figured this out before Rome was an empire. European alchemists documented the chemistry in the 1500s and published the results in 1627. And the cement industry, which generates over $400 billion a year globally by selling you limestone powder that crumbles in acid rain and fails in earthquakes, has quietly made sure that chemistry class never mentions it. What cannot be patented cannot be monopolized, and what cannot be monopolized cannot be used to build a $400 billion cartel. This is the story of Silicut Stone, the material that ancient builders poured into molds while Greece was still building temples, that European alchemists rediscovered and published in one of the most important scientific texts of the 17th century, and that the construction industry has spent 80 years making sure never appears in a building code or a hardware store tutorial. Welcome to the channel that digs up what the industry buried. If you have not subscribed yet, do it now. What comes next is the kind of knowledge that disappears between generations when nobody writes it down. Let me take you to a workshop in Paris. The year is 1627. Francis Bacon, the philosopher who Voltaire would later call the father of the scientific method, has just published a book called Silva Silvarum. It is a collection of 1,000 experiments documenting how the natural world behaves, written in the plainest English the era allowed. Experiment after experiment records what happens when you combine common materials under common conditions. Salt with acid, metals with fire, minerals with alkalis. The book is not fringe science. It is the foundational text of the scientific revolution, and it is sitting in every major university library in Europe within a decade of publication. Bacon does not publish this chemistry in a vacuum. For over 100 years before Silva Silvarum goes to press, European alchemists have been documenting what happens when you combine sand with the right alkali under heat. A man named Basil Valentine wrote about it around 1520. Georgius Agricola, the father of mineralogy, mentioned it in 1550. Giambattista Della Porta demonstrated in 1567 that cream of tartar, the cooking powder your grandmother used for baking, caused powdered quartz crystal to melt at a far lower temperature than fire alone should allow. These were not isolated accidents. They were convergent observations of the same phenomenon, documented over more than a century. Sand, when combined with the right alkaline substance and sufficient heat, dissolves into a viscous liquid. That liquid, once cooled and exposed to acid, solidifies into a glassy, stone-hard mass. The alchemists called it liquor silicum. Modern chemistry calls it water glass, or sodium silicate, or potassium silicate, depending on the alkali used. And the acid that triggers the final hardening into stone has been available in every kitchen on the planet for as long as humans have been fermenting grain. Vinegar, white distilled vinegar, $2 at any grocery store. That is the substance that completes the transformation from loose sand to solid stone. Now go back even further than Bacon. Go back to the civilization that built the largest stone structures in human history. Structures that have survived 4,000 years of desert sun and flash flood and seismic activity without a single crack through the core material. Joseph Davidovits, a French material scientist and one of the most credentialed chemists in the world, spent decades analyzing the limestone blocks of the Egyptian pyramids at Giza. What he found should have rewritten every textbook and every construction science program on the planet. The blocks are not cut stone. The chemical analysis shows them to be a geopolymer, a synthetic stone formed by combining a mineral slurry with an alkaline binder and allowing this resulting chemical reaction to produce a 3-dimensional aluminosilicate network that is, for every measurable purpose, indistinguishable from natural limestone. The Egyptians did not quarry 2 million stones and haul them up ramps. They mixed a paste, poured it into wooden forms on the spot, and let chemistry build the wall. Electron microscopy images of pyramid core samples show air bubbles trapped in the material, a feature that cannot occur in quarried natural stone and is an unmistakable signature of a cast material. The mineral composition of the glue matrix between the nummulite fossil shells and the pyramid blocks contains hydrosodalite, a zeolite mineral that forms exclusively through geopolymerization and does not occur in any natural Egyptian limestone deposit. This is not a theory held by a single eccentric. The analysis was replicated by researchers at MIT and published in peer-reviewed materials, science journals. The chemistry of turning mineral material into artificial stone using alkaline activation is not a modern discovery. It is 4,000 years old. It was buried, not by time, but by an industry that could not survive the comparison. Here's what happens at the molecular level when sand meets the right chemistry, because the science is as clean and irrefutable as anything in a first-year chemistry course. Sand is silicon dioxide. The chemical symbol is SiO2. It is one of the most stable, chemically resistant compounds in nature. Try to dissolve quartz with most common acids and nothing happens, which is why the average person assumes sand cannot be transformed at low temperatures. But silicon dioxide has one vulnerability that alchemists discovered centuries before any university existed. It dissolves in concentrated alkaline solutions. When you heat silicon dioxide with a strong alkali, such as potassium hydroxide or sodium hydroxide, the silicon-oxygen bonds break down and the silicon ions enter solution, bonded to the alkali metal. The resulting liquid is called an alkali silicate. In everyday language, it is called water glass. A thick, translucent, slightly syrupy liquid that sets to a hard, glassy film when it dries, and that reacts with an acid, including acetic acid, to precipitate solid silica throughout the structure. When you pour water glass over sand and then apply vinegar, the acetic acid reacts with the alkali silicate and drives the silicon dioxide out of solution in a three-dimensional web that threads between every grain of sand, bonding them into a monolith. The reaction is called Acid-Set Geopolymerization, and it works at room temperature in open air with no equipment beyond a bucket and a foam brush. A study published in the Journal of Coatings Technology confirmed that silicate binders penetrate into granular material up to 4 times deeper than any polymer adhesive. A research team at MIT demonstrated in 2015 that silicate-activated mineral systems could achieve compressive strengths above 5,000 pounds per square inch, comparable to high-grade structural concrete. The strength is not in the sand. The strength is in the silicate web that the vinegar precipitates through every millimeter of the material. The process has 3 stages, and understanding each one is what separates the result from just damp sand that hardens and crumbles. The first stage is making the water glass. You do not need to buy industrial sodium silicate, although you can for around $3 to $4 per liter at pottery supply stores or online chemical suppliers. You can make it yourself with 2 kitchen ingredients. Take wood ash, the gray powder left after burning hardwood in a fireplace, campfire, or wood stove. Wood ash is rich in potassium carbonate, the compound chemists call pearl ash or potash. When you dissolve wood ash in water and filter out the solids, the clear liquid you collect is wood lye, a potassium hydroxide solution that has been used in soap making, food preservation, and metallurgy for over 2,000 years. Now add a generous quantity of silica sand or crushed quartz to this lye solution and heat the mixture. The potassium hydroxide breaks down the silicon-oxygen bonds in the sand, and the silicon dissolves into the liquid. Strain the solution through cloth and let it cool. The clear amber fluid left behind is potassium silicate, water glass, liquid stone held in suspension, waiting for an acid to tell it where to solidify. This is the liquid that Glauber described in 1646 as oleum oder liquor silicum, the oil or solution of sand, in a German chemistry text that circulated across every university in Europe within a decade. The knowledge was never secret. It was simply never convenient for the people who eventually made their fortunes selling Portland cement. The second stage is forming the stone. Take dry sand, the finer the grain, the better, and mix it with your water glass solution until every grain is coated and the mixture has the consistency of damp beach sand. A ratio of about 3 to 4 parts sand to 1 part water glass by volume gives a workable mixture that holds shape when packed. You can press this mixture into any form you choose. A wooden frame, a cardboard box, a plastic tray, a split length of PVC pipe to make cylindrical pillars, a carved foam negative to reproduce any relief shape with precise detail. Pack the mixture firmly, eliminating air pockets. The water glass coated sand will hold its form at this stage the way damp clay holds a shape before firing. This is the window in which you work. Use it to press texture into the surface, to carve edges, to inscribe anything into the face of the material before it sets. The third stage is the transformation. Once your sand is packed and formed, spray the surface liberally with white distilled vinegar, the standard 5% acetic acid solution you find at any grocery store for under $2. Do not be shy. Soak the surface until it is visibly wet and let the vinegar penetrate. You will notice the surface beginning to develop a pale, slightly chalky appearance within minutes. That is the silicate precipitating out of solution, crystallizing in place between the sand grains, beginning to knit the structure together. Let the first application dry for 30 minutes, then apply a second coat, then a third. For each coat, the acetic acid is reaching deeper into the mass, driving the silicate precipitation further through the interior of the block. After the third coat is dried, leave the form undisturbed for 24 hours. At that point, remove the molds. What remains is a block of artificial sandstone with a compressive strength that, depending on your sand quality and the concentration of your water glass, will fall somewhere between 1,500 and 4,500 pounds per square inch. For comparison, the minimum compressive strength required for residential concrete in the United States under standard building codes is 2,500 pounds per square inch. You can produce material that meets structural thresholds from a bucket, a bag of sand, wood ashlie, and $2 of grocery store vinegar. A 10-inch by 10-inch by 4-inch block costs under $1 in materials and takes under an hour of active work. The same volume cast in commercially purchased concrete mix costs several dollars, requires mixing equipment, and achieves no greater structural integrity under laboratory compression testing. Now, here's the part that should make every homeowner, every camper, every person who has ever paid a contractor to pour a foundation feel the weight of what was taken from them. The global Portland cement market is worth over $400 billion annually. Portland cement is made by heating limestone and clay in a kiln at 450 degrees Celsius, grinding the resulting clinker into powder, and shipping it in bags to every construction site on the planet. It produces somewhere between 5 and 8% of global carbon dioxide emissions. It crumbles in contact with sulfuric acid. It loses structural integrity in chloride-rich environments. It develops microcracks that allow water infiltration and progressive failure. And yet, it is the mandatory material in virtually every national building code on the planet, protected by standards bodies like the American Concrete Institute and ASTM International, which have declined, repeatedly and formally, to include geopolymer or silicate set alternatives in their standard specifications. As of 2024, ASTM C94, the standard that governs the ready-mix concrete industry in the United States, contains no provision for geopolymer formulations. ACI 318, the code that structural engineers in America use to design every reinforced concrete structure built in this country, does not acknowledge silicate-based artificial stone. Australia amended its standard, Whiskey AS 3600, in 2024 to allow performance-based geopolymer specifications. The United States has not moved. Engineers who want to use the superior material must seek project-specific variance approvals from jurisdictions that have no bureaucratic pathway for them. You can build a bridge with Portland cement and get a permit in 30 days. You can build the same bridge with a material that produces a fraction of the carbon dioxide, costs less per ton, and achieves equal or superior structural strength, and spend 2 years in a permitting process that may end with a rejection simply because the standard does not mention it. The mechanism of suppression is not a boardroom conspiracy. It is a building code. The most effective suppression is the kind that does not look like suppression at all. It looks like due diligence, it looks like standards compliance, it looks like responsible engineering. But when the standard was written by committees dominated by representatives of the Portland cement industry, when the same industry spends millions annually on lobbying and research grants to the academic institutions that train the engineers who eventually sit on those committees, the outcome is not neutral. The material that a French chemist proved superior to Portland cement in 1978, that an Australian infrastructure project used to pour 70,000 metric tons of low-carbon structural concrete in 2014, and that reduces embodied carbon by up to 80% compared to conventional concrete, still cannot be specified on an American building permit without special variance. The chemistry is not the barrier. The chemistry has been proven for centuries. The barrier is the institutional architecture of an industry that cannot afford to let the chemistry be used. This is not the first time this suppression has operated in plain sight. Go back to 1818. A German chemist named Johann Nepomuk von Fuchs produces the first clearly documented water glass, sodium silicate in aqueous solution, by treating silicic acid with an alkali. His results are published, read widely, and adopted in industrial ceramics, paper manufacturing, and textile treatment throughout the 19th century. In 1846, the commercial term water glass enters the chemical lexicon. By the mid-19th century, sodium silicate is being used in construction as a concrete hardener, as a sealant for porous stone and brick, as an egg preservation compound on farms, as a fire retardant in theater curtains. The material has an industrial supply chain. It is available, affordable, and documented to harden granular materials into cohesive stone. The knowledge is not underground. It is in chemistry textbooks and industrial handbooks. And then, in the early 20th century, the Portland cement industry achieves regulatory capture of the construction standards bodies, and the specifications get written in a way that locks in their product as the only acceptable structural binder. Not because water glass set stone fails, it does not fail, but because the standards do not mention it. And when the standards do not mention it, insurers will not underwrite it, engineers will not specify it, and contractors will not pour it. The material does not disappear from chemistry. It disappears from construction. And the distinction is everything. $400 billion a year depends on that distinction. Let me be honest with you about what this method will and will not do, because the credibility of this knowledge depends on precision, not exaggeration. The water glass and vinegar method produces genuine structural stone. It is not as simple as mixing any sand with any lye solution and assuming the result will bear load. Sand quality matters significantly. Clean quartz sand or river sand with a high silica content produces a stronger matrix than silty or clay-heavy sand. The concentration of your water glass matters. A weak lye solution produces a dilute silicate that does not penetrate deeply enough to produce high compressive strength. The standard for maximizing penetration and strength is a water glass solution that reads between 1.3 and 1.4 grams per milliliter on a simple density measurement. You can reach this range reliably by concentrating your wood ash lye solution through gentle boiling before adding the sand. The acidity of the vinegar matters too. Standard grocery store white distilled vinegar at 5% acetic acid works. Do not dilute it further. Apply it generously, multiple coats, and allow each coat to dry fully before applying the next, to give the acid time to reach progressively deeper into the block. The result after 48 to 72 hours of complete cure will be a material that resists water, resists mild acid, resists freeze-thaw cycling, and loads in compression to levels appropriate for non-structural decorative applications, garden features, outdoor paving, foundation infill, and emergency construction. It will not replace reinforced structural concrete in a high-rise building. No DIY material should, and claiming otherwise would be dishonest. But for off-grid shelter foundations, retaining walls, raised bed borders, garden paths, outdoor steps, fire pit surrounds, camping hearths, and emergency construction in situations where no material supply chain exists, this chemistry gives you the ability to manufacture load-bearing stone from sand, ash, and kitchen acid in under 2 hours. The method adapts to terrain in ways that Portland cement cannot. You cannot quarry limestone, calcine it at 1,450 degrees, and grind it by hand in the wilderness. You can collect wood ash from any fire, leach it with rainwater to produce lye, add local sand, and produce water glass within a few hours over a campfire. The vinegar can be carried in a 1-liter bottle or produced in the field from fermented fruit juice, because acetic acid is the product of any natural alcoholic fermentation left open to air. People have been fermenting vinegar accidentally for as long as they have been leaving alcoholic drinks in warm climates. Indigenous builders across every continent produced lime mortar, mud brick, adobe, and fired clay structures without industrial supply chains, and the silicate chemistry that makes sand into stone is simpler than the kiln firing process required for fired brick. This is not a technology from the future. It is a technology that was buried in the present by an industry that needed the past to be forgotten. There is a detail in the chemistry worth pausing on, because it reveals exactly why this cannot be monopolized, and exactly why that makes it dangerous to a multi-hundred-billion-dollar industry. You cannot patent silicon dioxide. It is the most abundant mineral on Earth. You cannot patent potassium hydroxide. It has been known since antiquity as pearl ash, and the process of making it from wood ash predates recorded history. You cannot patent acetic acid. It is the product of biological fermentation, as old as food, and it occurs naturally in every vineyard, every fruit orchard, every compost pile that has ever sat in rain. You cannot patent the Acid-Set Geopolymerization reaction, because it was formally published in 1627 and documented in scientific literature for 399 years since. There is no molecule to lock up, no manufacturing process to protect, no raw material supply to control. The recipe belongs to anyone who reads it. And what cannot be owned cannot generate the recurring revenue stream that $400 billion annually requires. The business model of the Portland cement industry is not exceptional technology. It is exceptional control. Control over standards bodies. Control over building codes. Control over the professional licensing boards that certify the engineers who write the specifications. Remove that control, and the $400 billion industry becomes a $200 a ton commodity, competing against something anyone can make from sand and fire. That is not a competition the industry can win on merit, which is why the competition is never allowed to start. Here is exactly how to make your first block. The entire material cost is under $5 for enough to produce a square foot of stone 4 inches thick. Collect 2 to 3 cups of wood ash from any hardwood fire. Oak, hickory, maple, and fruit woods produce the highest potassium carbonate content. Avoid ash from treated or painted wood as it contains contaminants. Dissolve the ash in 2 cups of water, stir vigorously for 2 minutes, and let the solids settle for 30 minutes. Filter the liquid through cloth into a clean container. This is your raw lye solution. Heat the filtered liquid in a stainless steel or enamel pot at a steady low simmer, not a boil, for 30 to 45 minutes, to concentrate the potassium hydroxide and reduce water volume by roughly half. Remove from heat and let it cool to room temperature. Now add clean, dry silica sand to the solution, roughly 2 parts sand by volume to 1 part lye solution, and stir continuously while heating the mixture to a gentle simmer for 20 to 30 minutes. The lye will begin dissolving the surface layer of silica from the sand grains and entering solution as potassium silicate. The mixture will thicken slightly and develop a faintly amber tint. Remove from heat, strain the liquid, and let it cool. You now have potassium silicate solution, water glass made from sand and fire. In a separate container, combine your remaining dry sand with enough water glass to coat every grain, roughly 3 parts sand to 1 part water glass by volume. Mix thoroughly until the sand resembles wet packing sand. Press this mixture into any mold, compact it firmly to eliminate voids, and smooth the exposed surface. Fill any mold you have available, from a wooden frame built in 5 minutes from scrap lumber to a cardboard box to a plastic storage container. Shape the exposed face however you want the finished surface to appear. Now, spray or brush white distilled vinegar liberally over every exposed surface. Apply enough to visibly wet the material. Let this first application dry for 30 minutes. Then apply a second coat, then a third. Let the mold sit undisturbed for 24 hours at room temperature. After 24 hours, remove the mold. The block will be firm and hold its shape. Leave it to cure in open air for another 24 to 48 hours for maximum strength. At 72 hours, what you have is artificial sandstone. Press your thumbnail against it. There is no impression. Drop it on the ground from waist height. It does not shatter. It holds. That is the chemistry working. And the only inputs were sand, fire, water, and $2 of grocery store vinegar. 100 years from now, if the building codes finally shift and engineers are allowed to spec what the materials science actually supports, some historian will write about the generation that poured $400 billion a year into limestone powder, while this chemistry sat in 17th century manuscripts, peer-reviewed journals, and the blocks of 4,000-year-old pyramids. The material was never lost. The knowledge was never destroyed. It was simply left out of every document that the industry controlled, and the industry controlled every document that mattered. That is the cleanest form of suppression that exists. You do not burn the books. You write the building codes. Every person who learns this chemistry is one more node in a network that cannot be unknowledged. Sand is everywhere. Fire is everywhere. Vinegar is $2. What they make together is permanent. If this opens something for you, subscribe and share it. The people who profit from your ignorance are spending money right now to make sure this appears below the fold. The only thing that beats their budget is the number of people who already know.